In this video, we will discuss a paper which came out recently from Microsoft, and it's called FastFormers Highly Efficient Transformer Models for Natural Language Understanding. So first of all, transformer architectures have become like the state-of-art architectures for most of the NLP applications. But one of the problems with these architectures is that they're computationally very expensive, or their inference time is very high in many cases. In this paper, authors have proposed three techniques for handling that particular problem. One of the techniques is called knowledge distillation, the second is called structured pruning, and the third is called model quantization. And combining these techniques over the transformer architectures, they have shown that they can improve the inference time by around 233.9x or 9x improvement. So this is the range of improvement they've given. And this is on a CPU machine. They've also shown that on a GPU machine, this inference time can be improved by 12x times. So these are some really high improvements. They've also benchmarked that for 100 million requests on these devices, how much money you have to pay if you have this much improvement. So compared to the current baseline transformer architectures, they have shown that you will have a huge reduction in terms of your overall cost. So these are some of really amazing results, and we'll discuss more about what they have implemented and what they're proposing. So in terms of the introduction, essentially NLU is a very important problem in natural language processing, and towards solving this problem they are using transformer architectures. Now the first techniques which they have proposed is called knowledge distillation. Now what knowledge distillation does is it tries to prune the model. So essentially, let's say if we have a large model and we want to prune the model based on the make it a slightly smaller, but still want to make sure that the performance of the pruned model is still good enough. This is called knowledge distillation, and knowledge distillation uses something called a teacher student network, where there is a bigger teacher network which tries to teach the student network such that after training, the student network has a similar performance to the teacher network. The other technique they have used is called structured pruning. In structured pruning, the idea is that you want to reduce the number of weights in your network. So for example, in case of transformer architectures, we want to reduce the number of self-attention blocks or the number of overall heads. The final technique which they have used in this paper is called model quantization. And essentially the idea is that on a typical GPU machine, the default data type is 32-bit. But let's say if we use a 8-bit precision machine or a 16-bit precision, what will happen in that case? And they have shown that even if you use 8-bit or 16-bit precision, the model accuracy doesn't drop too much. So this is the general idea, and they have also provided an open source code base from the paper, so that's pretty good. So first of all, let's discuss knowledge distillation. So what is knowledge distillation? So knowledge distillation is nothing but a technique of model compression. The idea is that we have a teacher network. So let's say we have a general BERT network, which is of a very large size. So generally the BERT architecture is like has 12 stacked architectures, and similarly the other architectures which have came recently like Roberta or other architectures are like really massive or really big in their size. What we want to do is we want to design a smaller network which can have the same performance but slightly or much lesser number of parameters. So the student model they learn together with the teacher model, and the student model tries to mimic the performance of the teacher model. And in knowledge distillation, there are two techniques which are quite famous. The one of them is called task agnostic distillation. The other is called task specific distillation. In the task specific distillation, essentially what we are trying to do is we are trying to initialize the student network, and we are trying to fine tune both the teacher network and the student network on the task. And this is slightly different on task agnostic neural network, where we are initializing the student network, but we are only fine tuning the student network finally. They've given two architectures which are popular in knowledge distillation in this figure. As you can see, there is a general teacher network which is defined over here. Now what's happening over here is that general teacher network is trying to distill its knowledge to a student network, and then they are trying to fine tune themselves on a task specific parameter, and they've also given like how which thing is happening after what. The second approach they have proposed is called task agnostic distillation. Here, what happens is that the distillation happens before fine tuning. So, the fine tuning happens only on the student network. So, that is the general idea. So, what they have shown is that the distillation is very powerful, and even after distilling the network to a huge degree, they are able to still match the performance of the Roberta and BERT models, and both the task specific and task agnostic models are performing better, and the results they have proposed over here or shown over here are from the best model for both the cases. So as you can see, the BERT model is performing at around 75% on the teacher set, but the student model is also performing very comparably, or in some cases are slightly better than the teacher model, and that's the same is happening with the Roberta architectures as well. So that's pretty amazing. And so these are the results from the knowledge distillation experiments. The other thing which they are using is called structured pruning. So the idea in structured pruning is, so there is a very popular paper which came out last year, which is called lottery ticket hypothesis. And those are some of the papers which are very popular in structured pruning literature. So the idea is that in structured pruning, we are trying to prune the network while the model is still training. Okay, so essentially the idea is that in case of transformer architectures, we can prune some of the multi-head attention blocks. We can prune some of the feed-forward networks. And the idea is that we will define a target architecture size. So fine, because when we are doing structure pruning, we will say that this is our target architectures look like. This is the model specification we are expecting from this structure pruning experiment. So then what the structure pruning task will do, it will identify what are the least important components in the network, right? So that is the essentially the idea. What are the least important heads, or what are the least important hidden states in your network? Now the question is that how it will identify it. So the one of the methods which is popularly used is called a gradient based information retrieval or gradient based information extraction. So essentially what it tries to do is it tries to generate a feed forward and a backward propagation graph, and using that it tries to assign an importance weight to each component in the network, and then using this importance weighting it tries to decide if we want to prune this component or we don't want to prune this component. And the selection of the total number of components finally happens based on the number of specification in the target architectures. So if we have said that we want 3 parameters in the target architecture, if we want 1200 parameters in the target architecture, that information will be used when we are making these pruning decisions. Now, what they have also shown in this paper is that combining structure pruning and knowledge distillation also worked out really well. So, what they have done is they have done a pass of structured pruning, and then over the reduced network, they have done a second pass of knowledge distillation, where they have applied again the knowledge distillation technique to again fine tune the reduced network, and they have done a couple of passes over it. Now, after using structured pruning, they have proposed two kinds of results on multi-RC and record task datasets. On these datasets, they have shown a performance improvement of around 1.9 point accuracy, slightly decreasing accuracy, but the inference time is improving by 2.97%. And the overall architecture of the model is reducing by 50% of the heads and 75% of the immediate hidden states. So that's a significant improvement in terms of the inference time or in terms of the model size, but you are not losing too much on the accuracy. And they have also outlined some of the results from the structured pruning experiments. And as you can see, they have outlined what is the inference time, what is the time in terms of hours, and what is the pruning size, what is the network size. And you can see the accuracy is not decreasing too much, but our inference time is improving by a lot. And that same is happening for record task as well. But in case of the multi-RC task, the improvements are much more significant. Okay, so the final technique which they have proposed is called model quantization. In model quantization, as I explained before, they have used something called, rather than using the full 32-bit precision, let's use a 8-bit or 16-bit lower precision values and see if that can also improve the model. and they have shown that even that thing can also improve the model significantly. Finally, they have also done some ablation study in terms of adding different features, which we have discussed. So, for example, in this table 3, they have outlined like what is the performance of the baseline BERT model, and they have also specified like what is the cost or what is the time or what is the accuracy of these models. So, as you can see across the axis, if we are going down and as we are pruning models more and more, our accuracy is not decreasing by much. So from here to here, our accuracy is not even decreasing by 2%. It's close to 1.2%, I would say. But as we are adding different things, so the first thing is dynamic sequence length. So the first thing itself is giving them similar accuracy and reducing their time by around 3x times. The second technique is knowledge distillation. That itself is also reducing the time significantly. The other is 8-bit quantization and graph optimization. That is also significantly improving the performance. And the finally multi-instance inference is also improving a lot. And structure pruning, as you can see, is also improving, further improving the time it's taking, but accuracy is still remain the same. So the overall speed up is huge, but we are also saving both in terms of the cost and we are not losing anything on the accuracy. So these are some of the really important takeaway from this paper. And finally, they have shown this plot, and as you can see pictorially, the queries. This is the query time, and this is the how much query time each of these networks are taking. So the baseline out of the box model can only handle 4.45 queries uh, per second. But if you look at the structured prune network, which has the similar accuracy, but it can handle much more number of queries per second. So that's a pretty amazing advancement. So yeah, here's the paper, and I think it outlined very latest ideas and all the ideas from different techniques in machine learning in a one single paper, and they've also proven some really good results in both in terms of their overall inference time improvements and also these cost improvements. And thanks for watching this video. And if you liked similar videos, please subscribe to my channel and comment for more upcoming videos. Thanks a lot.